The nth partial sum of a geometric series, if we want to add the first n terms, we have this formula right here. A little bit more complicated than the arithmetic formula. I am not going to explain where that comes from or why that is the formula. Not that we couldn't make sense of it, but it would take a lot longer. And it really doesn't bring clarity to why the formula is what it is. That arithmetic is so nice. It's like how many pairs of what number. The formula really makes sense when you think of it that way. This formula does not have that sort of cool aspect to it. So here's the formula. Know the formula. Use the formula. I'm not going to explain why it's true. If you really want to know, we can talk about it, or you could probably find it on the internet. Okay, let's take a look at an example. Oh, looks like I did not fill that part in. That should be 9 over 2. My mistake. Find the sum of the first 5 terms. And this is what we know. A2 equals 1/2 and A4 equals 9/2. Just the first 5 terms, the geometric series and sequences, those numbers get big really quick, and especially when you start adding them. So just 5 terms will be plenty for us. Okay, we know this much. Kind of feels like the previous question, except these two are a little bit closer together. I think we had A3 and A7 before. So A2 and A4. All right, I'm going to start off the same way. I'm going to make my list here. Let me cover that part up. Not nearly as long, so I don't know A1. I know A2 is 1/2. I don't know A3. I know A4 is 9 over 2. So there are 2 leaps from A2 to A4. I multiply by R twice to get from 1/2 to 9 over 2. So let me set up a formula, or an equation, I should say. If I begin with 1/2, multiply by R twice, R squared, I end at 9 over 2. And let me go ahead and solve this quickly, and you might be able to see what it is already. And okay, so multiplying both sides by 2, right? That cancels those denominators. So I get R squared equals 9. Taking a square root, I get 3. Okay, so the R is 3. So I'll say, okay, well, knowing R is really good, but I also need to know A1. So if you go back to the formula, R appears twice. Then we have A1, and how many terms that we're summing, right? N. So very different formula, right? A1, and then this big fraction. Yeah, not going to explain it. Okay, so what is A1? Well, we can kind of do that backwards thing, right? So if A2 is 1/2, then if we work backwards with R equals 3, we should divide. That will give us A1 equals 1/6. All right, 1/2 divided by 3. If you're not comfortable with that, hey, grab a calculator, right? Or think of it as multiplying by 1/3. Dividing by 3 is the same as multiplying by 1/3. All right, in any case, we've got R is 3. We've got A1, and we want the first 5 terms. So, I've got it just kind of going down the page right over here. The formula, since I can't fit it all on the screen at once, S sub n, A1 times this big fraction, 1 minus R to the n over 1 minus R. A1 is 1/6. Then we've got times fraction 1 minus 3 to the 5th, because we're doing the sum of the first 5 terms, S5, over 1 minus 3. I recommend put this whole thing into your calculator in one shot. You don't want to round anything. because that'll throw off the sum a little bit. Just put that whole thing in at once, and you'll notice that it ends, it's 4,920.66667. That 0.66667 is 2/3. So there is your fifth partial sum. And generally these end up with some fractions involved. It's not uncommon, or at least really big numbers at the least. Okay, let's move on to one last topic when it comes to geometric series. Now, geometric series have this really interesting property that we just can't ignore. Let me introduce that to you just with this sequence right here. A sub n equals 81 times 1/3 raised to the n minus 1. All right, what am I going to do with that? I just want to explain something first, and then we're going to look at the details. It turns out if r is between -1 and 1, somewhere between there, it might be positive, it might be negative. We have a positive. Whatever the case, it's less than 1, and it's not less than -1. Okay, so we've got 1/3. When r falls between -1 and 1, then as we keep multiplying by that r, the terms get smaller. Okay, so we're going to do that for this sequence in a moment. But even if it was negative, right, then the terms would be getting less and less and less each time. Okay, what does that mean? If the terms are getting smaller really fast, if you were to add all infinitely many terms together, the total sum of all of those infinitely many terms would be finite. You think that's impossible. How can you add infinitely many numbers together and it not add up to infinity? Well, I'll show you. If you add all infinitely many terms to this sequence, it won't go into infinity. It'll start to get bigger, and then it'll level off. And you'll still be adding, more and more numbers on, but those numbers are going to be so tiny that I think leveling off is a good way of explaining it. Okay, let's investigate a little further with this sequence right there. So I'm going to find, let me just show you part of this. Just focus on one piece here. Here's A1 through A5. Okay, A1 is 81. A2, now we start multiplying by 1/3. Multiply by 1/3, multiply by 1/3, multiply by 1/3. Same as dividing by 3. 81, 27, 9, 3, 1. Those are the first 5 terms. If you add these 5 terms together, you get 121. You can easily check that if you want. You get 121 when you add the first 5. You think, okay, wow, it's adding up pretty quick. What would happen if you found more terms and kept adding them? So here's A6 through A10, just the next 5 terms. Well, we keep dividing by 3, multiplying by 1/3, right? Each time. So taking the next one, multiplying by 1/3, multiplying by 1/3, multiplying by 1/3, and so on and so on. 1/3, 1/9, 1 over 27, 1 over 81, 1 over 243. Okay. These are getting small really, really fast. If you add these 5 terms together, it's not even 1. Less than 1 when you add all of those together. Actually, it's not even 0.5. I put less than 1 just to make it easy, but it's not even a half when you add all those. We added these first 5, and we were already up to 121. But the next 5, you don't even get one more. Now, of course, this sequence doesn't end there. Plus, there's still infinitely many more terms to be added. But even if you kept adding more and more, those numbers get so tiny that you're hardly adding anything. And even if you kept adding all infinitely many, these from here would not even get to 1. Keep adding more and more terms. You'll never even get to 1 when you put all those together. Okay. What do they add up to then? Right? That's the question. Let's investigate that. Here's another formula. This is the sum of the infinite geometric series when you add all infinitely many terms together. Turns out this formula is much simpler than the nth partial sum. We just call it capital S because we're adding all infinitely many terms. It equals the first term divided by 1 minus r. Very simple. There's a similarity, right? I think the other one, a1, 1 minus r to the n over 1 minus r. So these parts, these parts are the same. This part is gone though when you add all infinitely many. Anyway, not that that's a big deal, but okay. Now, this isn't true always. It's only true when r falls between -1 and +1. Or you might say when the absolute value of r is less than 1, which is what we had in this example. We had 1/3. But if it was -1/3, something similar would happen. Okay, let's take a look here. Let's continue with that discussion about 81 1/3 to the n minus 1. What if we found the sum of all infinitely many terms? Well, let's use our formula. There's a1, there's r, so 81 over 1 minus 1/3. Before you grab a calculator, 1 minus 1/3 is 2/3. So it's 81 divided by 2/3. Now grab your calculator. Be careful, you need parentheses around that denominator. And you will get 121.5. And this should just blow you away. The first 5 terms are 121. After that, starting at the 6th term and going infinitely more, it's just 0.5. That is crazy. Okay. Here's a really interesting application. So you'll get questions like this in homework. Find the sum of the infinite geometric series. Boom, formula, boom, boom. You'll get it. You'll see positive values of r and negative values of r. Be careful when you plug in here to always subtract. Even if you're subtracting a negative, then it will become addition, right? Okay. But I want to get to this interesting example. Convert to a fraction. We can use that formula for the geometric series to turn these infinitely repeating decimals into their fractional form. Okay, so let's look at 0.23 with the bar. And if you guys, as you probably know, the bar means those repeat. So this would mean 0.23, 23, 23, and so on. We're going to represent that infinitely long decimal with a geometric series. Okay, think of it this way. 0.23, 23, 23. Think of it like this: 0.23 plus 0.0023 plus 0.000023. And right, as you kept adding these together, it's like they keep, the next one sticks on another 2, 3 on to the end. And if you add infinitely many of them, then you'll have that infinitely long decimal, right? Okay, so looking at this, that's a geometric series. The first term is 0.23. What do you keep multiplying by each time to get the next one? 0.01. So 0.23 times 0.01 would get you from here to here, and then multiply by 0.01 again. It'll move the decimal place twice to there. Okay. So if we're moving 2 decimal places, 0.01 will do that. Okay, let's put that in. There it is as a geometric series, right? 0.23 times 0.01 to the n minus 1. That number is definitely less than 1. It's between -1 and 1. So we can use our formula. Okay, A1 is 0.23, R 0.01, A1 over 1 minus R, 0.23 over 1 minus 0.01. Let's do the denominator first. That's 0.99, 0.23 over 0.99. Well, if we move the decimal, multiply top and bottom by 100, or put that in a calculator and hit the little double arrow convert to a fraction, it's 23 over 99. There's the fractional form of 0.23 with the bar. And just in case, I know you got a calculator there you could check, but let's do it. 23 over 99, 0.23232323 going on. That is a great way to conclude this chapter and this set of sections for exam number 4. Okay, check out the homework. See you in the live meeting.